Hello everybody, I'm Professor Ann White from the Department of Nuclear Science and Engineering here at MIT. This is the first of 4 preparatory lectures for a seminar, a lecture in 22081 Sustainable Energy on AC circuits. In this first lecture, what we're going to go over are some of the fundamental circuit elements that we use in AC circuits. And these are the energy storage elements, the capacitor and the inductor. They're going to be really useful later on when we talk about energy storage and energy transmission in AC power systems. I want to sort of make a note that if anyone's really getting interested about the circuits that we discuss in these little sub-lectures today, you can go back and sort of take another class at MIT 22071, which is an introductory course on electronics, as all of the lecture notes here were adapted from Professor Hutchinson's notes for that course. So now let's go ahead and start here on our notes to the pad of paper, talking about our 2 circuit storage elements. So the first one is our capacitor. When you look at a circuit diagram, you're going to see that a capacitor is drawn as 2 parallel lines with the leads connecting top and bottom. What you'll also notice when you see the capacitor in a circuit diagram is that it's going to have a labeled polarity. So the top will be labeled with a plus for positive, and the minus will be labeled with a minus for negative. So we're now going to bias the capacitor by putting a voltage drop across the 2 parallel plates. So we denote that just by writing a little V for a voltage drop across them. Now, to keep our polarities consistent in our circuits, we're also going to draw the direction of the flow of current, which we denote by an arrow flowing down from the positive to the negative, and we give this our variable I. So our capacitor is going to be storing charge on these parallel plates as we put a voltage drop across it. So that means we can now write down the operational equations for our capacitor. So let's go and write those down. Our operational equations are that the voltage drop across the capacitor is equal to the stored charge, which we'll note with Q, divided by the capacitance. So V equals Q divided by C. Now we can also write this, because charge is related to current, we can also write this operational equation as voltage equals 1 over the capacitance, 1 over C, multiplied by the integral of the current with respect to time. We could, of course, reverse this operational equation and relate the current and voltage differently by writing the current flowing through our capacitor, I, is just equal to the time derivative of the charge, dq dt, by our identity, which is then equal to the capacitance, C, times dV dt. So now we can also note the key element here, which is for our capacitor, our stored charge Q, is equal to our capacitance, capital C, times the voltage drop across the capacitor. So Q equals capital C times our voltage. So as an aside here, if you find yourself looking at a circuit diagram as part of your work or part of your research, you might notice that sometimes there's 2 different versions of how a capacitor circuit element is drawn. So let's go now to the notes and write a little aside about that, just to help you out, as you might see these sometimes in your future journeys in circuits. So these 2 different types of the circuit elements that you see in the diagrams are coming about because there's 2 main types of capacitors. The first main type will be drawn just as we have, with 2 parallel lines with plus or minus. And when it's drawn like this, it doesn't matter which polarity you use when you connect the capacitor in the circuit diagram. This is a bipolar or an unpolarized capacitor. But sometimes you'll see the capacitor element drawn with a curved line and 1 straight line instead of 2 straight lines. So that will look like so. And in this situation, what this is telling you is that this particular capacitor is actually a polar capacitor. So it is typically an electrolytic capacitor, And it must be connected in the circuit with a particular polarization. So you have to make sure that you connect the vertical straight line to the positive and the curved line to the negative polarity. So let's move away from that aside and move to the next important reason we're talking about capacitors in this lecture on AC circuits. So I'm just going to change my notes now and move to the next page. I think I have to rip this off, right? So I avoid the shadow. Sorry. So I just really pull this guy. Wow. Okay, there we go. So why are we introducing capacitors in this lecture on AC circuits, energy storage, and transmission? Well, that's because capacitors are going to play a role in our larger systems because they can store energy in the electric field. And so this is sort of the way we want to think about this is let's just write this down. Let's go to our notes and just write down this important point. For our capacitors. So what we're doing is by charging our capacitor, we're delivering energy to the capacitor.
Okay. Yeah. Okay, we're going to hold for a minute.